And finally, we have Rupeng today. Many of you may not be familiar with this topic, Vector-Symbolic Architectures, VSA. So we're actually gonna most likely have a tutorial on this in the summer school. This general class of methods, which actually has a long history and is a very interesting different branch of Neuro-Symbolic AI, if you haven't heard of it. It does have this particular, or the most expensive part of it, I think, is exactly what Rupeng is going to talk about. All right, and here's info on our speaker, Rupeng. And this paper was published in NESI last year, and you can find out more about his work here. And we can put this on Discord if you want. Okay, and as usual, you can ask questions in multiple places, and we'll transmit them to the speaker during the session. And next week, we have Nichesh, so looking forward to that. All right, and with that...
Sorry, I also think we can announce that about a month before the summer school, we plan to stop these weekly sessions just to have some kind of break for everyone. So yeah, we will have 2 or 3 more of these sessions, and then it will be kind of a summer break for everyone before the summer school.
Yes. Summer break before the summer school. So just a few more sessions, and then we'll gear up for the summer school. All right, and with that, go ahead and take it away, Rupeng.
Okay, thank you. So let's get started. So thank you for inviting me. I'm very honored. My name is Ruipeng Liu from Syracuse University. I'm currently a PhD student, just finished the 4th year, advised by Garrett Cards, Dr. Garrett Cards from my university. He's a associate professor, and today I'm going to talk about my last year's paper published in NESI 2025, Linearithmic cleanups for vector-symbolic key-value memories with Kroneker rotation products. And below is listed the co-authors. The first one is obviously me, and the last one, or actually the rightmost one, is my advisor. So just a bit of a background stories of my research area. So currently we are interested in this differential data structures and memory sort of area. So under this umbrella terms, we have multiple models that has been either very ancient or very new, and it depends on when you look at it. So starting with this Huffy network, that is essentially a neural network structure that act as a sort of like a read-and-write memories to store data into that in a single pass learning manner. And following by that, we have something like a transformer model, which is the foundation of the current large language models, where you have each of those blocks called the transitional blocks, and within each of those transformer block, we have KQV matrices acting as a queries of in some way like a memory structure here. So that's another area that we find maybe related to this umbrella topic. There are many other more related or more directly related topics, such as this model called Neuro-Turing machine, developed, I believe, by Google DeepMind or something like that. It is essentially an emulation of the Turing machine that we all know about it. Here, different from the Turing machine, here we have a memory that is no longer a infinite length tape, rather it is a matrix, and the controller and has essentially the controller and has from the Turing machine, except they are implemented by neural networks, so that the controller controls has to read from or write into the memories to specific locations. And following by that is one of my advisor's work that is called a Neuro-Turing machine. It's called a neural virtual machine. So instead of emulating a simple Neuro-Turing machine, Turing machine structure, this one, the neural virtual machine, or in short NVM, actually emulates the Harvard architecture that our current physical computers every day uses. So we have registers, we have all kinds of memory structures inside of it. And it is a self-recurrent model that can work over time. And it has not one, but actually three different separate memory structures that can handle a variety of different tasks, such as, well, similar to Turing machines, it can handle the read and write operations, but also it can also handle point arithmetic, such as dereferencing, referencing, or increments and decrements. So my work actually starts with the studies of the neural virtual machines memory structures here. So let's dive into the neural virtual machines memory for a moment here. So the memory of a neural virtual machine is essentially a square matrix of n by n, denoted as M here. So once we have a address so that we wanted to read data from the memory, then we perform this operation here. Essentially a matrix vector products between the memory and the address vectors, and then the result of that is passing through a treated as an activation function, so that we maintain the range of the output of that value. And the function sigma here can be either a sine function or a sigmoid function for a better continuities. That because the NVM is essentially an end-to-end trainable model. So that is the read operation. And followed by that, we also have to have the write operation here. So this is not just writing data into memory. Rather, it is what we call as an overwrite operation. That first we have to erase. Assume that we're given an address that we want to write values into. Then the first thing we wanted to do is that we have to erase whatever has been stored before in that address. And then after that, we could write the new values into that. So the erase operation basically contains a read operation followed by the actual erase operation here. So if I draw the dimensionality of each data structure here, so M again is a square matrix, and the address is a vector of dimension n. Also, the value vectors is also of a vector of the dimension n here. So as we can see that from the read and write operations, we have a series of inner products between a square matrix and the vector. Also, we have some outer products between vectors of the same dimensions. So that brought essentially two problems that we wanted to work with. So first of all, the capacity of the memory itself is essentially n because it is a n by n matrix, and since our data is in dimension n as well, so at most we could store n different data into the memory. And so starting from there, we were thinking, is it possible for us to change the structure of the memory so that it can preserve the single pass learning capacity, single pass learning feature, such that in the matrix form we just have to see the data for once, and then that data is stored correctly in the matrix. So comparing to the nowadays the neural networks iterative learning procedures, where you have to train the data over and over again so that the model can learn the data. Here, we wanted to preserve the single pass learning features from that. Also, we wanted to expand the capacity of the memory so that we can store more data as much as possible, which is going to be very efficient. So the starting sort of ours would be replacing the memory structure from a matrix to something like a Hopf network, or essentially a neural network structures to store the data into that particular network. And that leads to us to seek for if there's any single pass full capacity learning rule, and that generates the papers we published in ICML 2024. And short conclusion is that such single pass full capacity learning rule, under some assumptions of ours, doesn't exist. Which I'm not going to cover that today. Rather, I'm going to cover the other problems. But should you're interested, I recommend you read about that paper. I find it quite interesting here. So the other problems that we find is that, remember that we have a series of inner products and outer products in the read and write operations in the current NVM memory. These operations, well, needless to say, cost quadratic times. And since NVM itself is a recurrence model that works throughout time, so and we wanted to preserve the end-to-end differentiability of that model. So once you're doing the backpropagation through time, then if you have each and every single time step has a quadratic runtimes of those operations, then that's going to be very expensive. So we wanted to remedy that or mitigate that. And again, by, of course, changing the structure of the memory. And the one that we find is Vector-Symbolic Architecture, by which I mean that using VSA, short for Vector-Symbolic Architectures, to form the memory such that it might mitigate the quadratic runtimes in the read and write operations. And that is, again, this talk is going to be about. So what exactly is a vector-symbolic architecture? Well, I consider that as a representation of concepts and their associations. So take a look at this very examples. We have a concept called a red pen, which consists of an associations between two concepts, red and pen. So what VSA do in the first place is that we first project these concepts into the same high-dimensional planes, represented by two randomly selected vectors there. So in this case, red is represented by U and pen is represented by V. So if you have multiple concepts that you wish to do associations and representations, then essentially you're forming a codebook. That is, if you collect those randomly sampled vectors from the same high-dimensional space. Then you wanted to do the associations between those concepts. So the way to do that is by this binding operator. It is essentially an arithmetic operations that is done to those vectors. And different VSA methods have different binding methods. And needless to say that you might have more than one such pairs of bindings. So the result of a collection of those bindings resulting in a single vector is called superpositioning. And once we have that, a collection of those bindings, sometimes you wanted to retrieve some of those values that given their keys. Say, for example, I wanted to retrieve the value vk here. So because I'm binding uk with vk, then uk, the vector, is considered to be a key of vk here. So the operations to retrieve that value out using a key provided is called unbinding. And of course, a variety of different VSA methods can have different implementation of those. So, but it's essentially unbinding, like binding and superpositioning is also an arithmetic operations here. So again, as I mentioned before, that there are many VSA methods there. Then the one that we choose to test it on is called holographic reduced representation. It is a very old paper, I believe, from 1997 or something like that. So here, the binding is defined as a circular convolution, and unbinding is defined as a circular correlation. Essentially, you could treat it as an inverse process of the circular convolution. And where we have here is, and last but not least, the operation that has been provided is superpositioning. That is implemented by element-wise addition, as shown in the slides here. So given that once we form the memory using the holographic reduced representations, or in short HRRs, then that would result in the memory from shaping from this square matrix, where the read and write involves a series of inner products and outer products, to the following. So since the HR has this binding operations defined as a circular convolution, which means that the result of that is actually the same dimension as your input vectors, by which I mean that it's the same dimensions as the address vectors and value vectors. So that the memory is of the same size of the input vectors, which is good. And reading operation is defined as the address is unbind from the memory, and writing operation is defined as address bind with a value and then adding it into the memory. So here I must mention that in the original HR papers, the vanilla way of doing circular correlations and circular convolutions is, technically speaking, taking quadratic times. Yet modern literature suggests that we could use fast Fourier transforms to do that, where the binding is implemented directly using fast Fourier transform, or FFT in short, and the unbinding is implemented by let's say the memory is binding with an address. So the unbinding is implemented by the memory binding with the quote-unquote inverse of that address. And that inverse of the address can be defined as a variety of ways. The point is, the read and write operations, if implemented by fast-forward transforms, it can be the time complexity of that can be decreases from quadratic times to basically n log n times, which means that it is possible for us to form a memory efficiently in the read and write operations using the HRs, theoretically speaking. So it seems perfect, right? So, but actually it has some limitations here, or actually a, well, shall we say features there? So once we have defined the memories in the form using HRs, then the reading operation is as follows. But technically speaking, the unbinding result doesn't use the correct or the accurate vectors that we wanted to retrieve. Instead, we retrieve this VK vectors out, which contains noise. And the noise is, according to the HR's definition, if you're doing that in a discrete way, then that's basically a scaled and shifted version of the original vector. So you need to have some ways to clean that vector up so that you can obtain the true or the correct vectors that you wanted to achieve. So this process is called cleanups, and the most vanilla ways to do that is by a inner product between the codebook and the current vectors that you have retrieved. Where here H we denoted as codebook. So right now here is the problem, because we wanted to mitigate the quadratic runtimes in the previous form, the matrix form of the memory. Here, technically speaking, the cleanup itself is taking quadratic times because it is essentially a matrix vector inner product. So how to remedy that? Well, we find that technically speaking, you need only to tweak the codebook for a bit, by which I mean that you basically create a new codebook. And that's where I introduce our method. It is the Kroneker rotation product codebook, or in short, CROPS. So what does this mean? Well, this is, we take the inspirations of the Hadamard matrix formulations using the Sylvester constructions and apply the Kroneker products to that using this rotation matrix as shown on the screen. I believe if any of those audiences in the here has some experience in robotics controls, then you should be familiar with this kind of matrix. So again, this is a recursive way to you could treat it as a recursive way to create each level, quote unquote, of the codebook, and for each levels, those trigonometries operate, trigonometries functions serving as the coefficients has an input theta here for each level, and each levels of those theta k parameters are uniformly sampled from one period of the trigonometries functions, so that we could provide some randomness to our vectors to our vectors in the codebook. And of course, the random sample ranges from 0 to 2 pi. So that's that. So this codebook, technically speaking, has a variety of merits that we find. And the first of all is that you don't have to store the entire matrix in the memory so that to know to know what the codebook is. And the reason why, and actually we find you need only to have a log n space storage for that entire codebook. And the reason why is because of the structure of that codebook. So again, here is the codebook. Believe me, this is a square matrix, has n rows and also n columns. So if you take a look at here in details, all these red parts are a sub-level of that codebook that generated from the previous quote-unquote recursive call. So these red sub-codebooks are exactly the same. So technically speaking, you don't need to remember any one of those, as well as those trigonometries functions, because those trigonometries functions are there no matter which levels that you're currently working on, because it is a Kroneker rotation product, as well as the negative signs on the bottom right corner. That you don't have to remember that. So neither of those red and blue parts you need to memorize. So only those theta values that you need to memorize. Well, how many of those? Well, of course, log n of those from theta 0 to theta k minus 1, because the length of the vector is n, and then you have like k levels of that, so that's log n. Easy. So that's one merit, but only storing those, sometimes you have to retrieve some some vectors from those codebook. If you are doing the way that you reconstruct the entire codebook and then extract just one column or one row out of it, it's going to be very inefficient. So we find that it has a second merit that, technically speaking, you don't need to reconstruct the entire codebook in order for you to retrieve just one vector. Instead, once you know the quote-unquote index of that vector, then you could retrieve that vectors via this reconstruction process in linear time. And the reason is as follows. So this is our codebook in a square matrix form. So as we've seen before, that this codebook is very structured data, so that each of these so that this codebook can be quote-unquote being divided into 4 parts, that is top left, top right, bottom left, and bottom right. Each of these sub-areas consist of exactly the same sub-level codebook, as well as a fixed trigonometric coefficient given the corresponding parameter theta k. So assume that we wanted to retrieve a retrieve a row vector here. So assume we wanted to retrieve the ith row. If you wanted to retrieve the ith column, then that's going to be similar to that. But so here I'm just going to explain how to retrieve the ith row here. So if you take a look at that, then the ith row can be in either of these following occasions. Either it exists in the top half of this current codebook or the bottom half of this current codebook. And since each region is very structured, therefore, as long as you know what the current level theta is, then as long as you know what is the corresponding vectors from that sublevel codebook, then duplicating by that and multiply that by that sub-vectors by the corresponding trigonometric coefficients, then concat them together would result in the desired row vector that you wanted to retrieve. So we need only to work on half of the vector itself. And as you probably already noticed, that the sub-level codebook of this current level is also a very structured data because it is a recurrence model, because it is a recurrence formulation, so that we could do the same thing here. This time it is, in this case, on the top half rather than the bottom half of the current level codebook, and then we can do the divisions on and on and on. So essentially speaking, you need only to figure out the index of the current vector, so that we could determine where exactly is this current vector's lands. Is it in the top half of the codebook or the bottom half of the codebook? Once we know that, we know the trigonometric coefficient of that, and then we could gradually work this vectors out from the base case all the way up to the current dimension. So it is, of course, a geometric sum, but then since there's only log n items, that result in the total runtime of the linear time process. So which is very good, correct? But I haven't gone to the sweet part, and that's basically our major contribution. Is that, remember that back in what I just been talking before, that the cleanup process is taking quadratic times, and the reason why we designed this codebook is we wanted to mitigate the quadratic runtime of the cleanup process. So here's why. Actually, in this codebook, we only need a big O(n) log n runtime to do the cleanups, and the reason is as follows. Assume that we have a codebook of h tilde k, and we have already retrieved the vectors from the superposition or the memory, and the vector is called uk here. So we do the canonical form of the inner products between the codebook and the vector. And because our codebook is very structured, so here, while doing this inner product, we don't have to do that in a brute force way. Instead, we could separate the uk into 2 halves, bottom half and top half, by the index of them, so that it can form 2 different vectors. One of them is called uk hat, which represents the top half of the vector uk, and the other one is called uk check, that is the bottom half of the uk. So once we have done that, after you do the matrix vector multiplications, inner product sort of stuff, and when you isolate the common term which in this case is going to be h to the k minus 1, which is essentially the sub-level codebook, you're going to have something like this. Partition the problems essentially into 2 parts, and that's basically each part of them is basically a sub-level codebook, which is also going to be a square matrix, and of course structured, and multiplied or actually inner product with a vector that is half of the size of the UK. The U subscript 0 k minus 1 and U subscript 1 k minus 1 is a linear combinations between UK hat and UK check by multiplying by their corresponding trigonometrics coefficients. So that's the first division. And then for each of those subproblems, you could also divide that further, because each of those subcodebooks are very structured. And of course, you could easily divide a vector into 2 parts by the index, and such procedure can be done furthermore. So essentially speaking, we are doing this divide and conquer process in the inner product sessions. So once we have done, once we have reached the base case of that, which is essentially reaching the base case of that codebook, then we result in this n-dimensional vector. And then the last step is we just have to take the argmax of that vector, so that it is going to be, so that we can obtain the vector UK after the cleanup. And obviously, this process is going to be taking big O and log n time, right? So, theoretically speaking, our method should have a very good, should have a very nice runtimes once the dimension of the vectors has been very large. So let's jump to the some experiment, but because these are all just theoretical results. And the experiments, the first experiment is we were trying to test exactly how much faster our method compared to the direct matrix vectors inner product. So, and the way that we tested that is that we have we have the same codebook doing different cleanup methods or different inner product methods. So the crop is our codebook with the divide and conquer cleanup method, and the direct is basically the same codebook doing the inner product of that vectors in a brute force way. So this is the result figure, and as we can see here, the x-axis is basically the log scale of our vector size, and y-axis is basically the runtime in seconds. How quickly does this cleanup process actually been taken? So from this figure, we could see that when the dimension of the vector is not large, aka means that it is below 2 to the power of 10, our method doesn't outperforms or is taking longer time comparing to the direct matrix vector multiplications. Yet, however, once the vector size is large enough, in this case above 2 to the power of 10, then that is our method really shines here, because our method, well, clearly increases the runtime of that process of cleanup clearly increases much more slower than the direct matrix vector multiplications here. So that essentially means that our method can scale better in terms of the cleanup times. So that's very good. So that provides the empirical result of that. It is possible for us to build a memory based on the HRs with a reliable cleanup method. So how exactly is the HR from the memory using the crop codebook actually performs? That's our next question. So we have this next test here that is called a memory capacity test. Basically means that once we have the HR memory formed using our method, how likely is one data being stored in that memory being correctly retrieved? Which is very important, because otherwise, if your memory can't retrieve the correct data, then your memory is essentially not working. And since we wanted to integrate our memories into a neural network architecture, in this case NVM, or potentially other architectures, if your memory is not reliable, then the neural part of that model is going to be really difficult to train. So we have to make sure that, or we have to test like how reliable is our memory performing. So the test is performed in the following manner. So first of all, since our memory is formed in using HR, which is a VSA method, we have to first of all project those address and vectors into the same dimension of spaces, which means that for both parties of those inputs, you need some sort of like a codebook. And here we chose the address codebook to be a Gaussian to be a sample from a Gaussian distribution. Essentially, a zero-centered covariance matrix is diagonal, and each entry is 1 over n, where n is the dimension of the vector. Actually, this Gaussian distribution is directly being taken from the HR's original paper. And furthermore, we assume that the address codebook has a limited address space, which basically means that you can't infinitely append as many data as you want into the memory itself. So that's for the address codebook. We also need a value codebook, and here we select essentially 4 different codebooks for us to test on. The leftmost is the same as the address codebook, and followed by that is what we call a binary codebook, which has also been taken from the HR's original paper, where this is essentially a plus and minus 1 binary vector with n dimension, of course, and then you normalize the vector's length to unit length. That's why you have this 1 over square root of n coefficient here. And third codebook is a Hadamard matrix, essentially. That is, we select those value vectors from a Hadamard matrix, or in other words, treating the Hadamard matrix as a standalone codebook. And last but not least is our codebook, which is similar to Hadamard matrix, yet however, during the Kroneker projects, we multiplied a rotation matrix there. So that's the setup of the experiments. Let's go to the procedure of the experiment itself. So the procedure of that is we first generate what we call a reference memory, that is in a matrix form denoted by the capital M here, that we store n values into the matrix, and each of them corresponding to an address which corresponds to a vector. Once we have done that, we write each and every single pairs of those address and value vectors into the middle memory, which is formed by HR here. Here, I'm going to call it HR formed memory. So once every single data has been written into the memory, we're going to read that out again, forming a new matrix n prime here. So of course, we don't know how reliable that the readout is going to be even after cleanup. So we denote each and every single one of those readout values as v primes. Once we have this n and n primes, we could compare these two memories, basically comparing the readout of the HR from the memories with the reference memory to see how likely each entry has been read out correctly by the following equation. Here we call it retrieval rate or success rate. So that's basically the experimental procedure. Now let's jump to the result of the experiments. So this is essentially the result of the experiments. So it is two separate ones. So let's start with the left two figures. So the leftmost figure is a test on the memory address space of 2. How well would each and every one of those value codebooks performs in a variety of vector length? So as we can see here, our method, which is the crop denoted as circles, didn't perform well when the dimensionality is low. But then once the dimensionality is quote unquote getting high enough, I believe the value here is 2 to the power 8, then our method can achieve 100% retrieval rates. Whereas the similar things happens to the normal, well, the Gaussian codebook and also the binary codebook. And the worst performing one is actually the Hadamard matrix codebook. And once the the address space is increased from 2 to 64, then the Sylvester's or the Hadamard codebook doesn't work at all. And our method can not only work on a high dimension as well, but also maintains a very high retrieval rate, which means that at least for this read and write operations, for one time, our memory is reliable as long as your memory, as long as your matrix, your vector size is large enough. So we also did a test of basically for for a given size of vector, how large can your memory be before the retrieval rate drops below 0? That's basically we call a capacity test, which resulted in the rightmost figure. And we could see that in a low dimension features, our method even outperforms the Hadamard matrix one. It's not as good as the normal or binary, or basically means this Gaussian or binary codebook, but it can actually works in a high dimension of vectors, resulting in a much higher capacity of it. So which is good. But this test alone, it doesn't make our method a good memory, because as we all know that memory doesn't involves just one time of a read and write process. It involves a sequence a sequential read and write process throughout the time. So we have to make sure that our memory actually works in that scenario as well. That brought us to the final experiments that we have done for the paper, which is called a multiple key value memory test. Basically means that should there be any errors in between the read and write, is that error going to be accumulated through time, or is that error going to be mitigated through time? So that's basically a reliability test, another reliability test on the memory. So the procedure is that, first of all, we use essentially the same codebook, except we don't test the Hadamard matrix codebook anymore, because essentially that is because in any of those tests, the Hadamard matrix codebook is performing worse than ours. So back to the procedure of the multiple key value memory test. So the procedure of that is basically we have generated a address, or selected one address and selected one values for the values to be written into that address for each time step. And then we write that into basically two memories. One of them is a reference memory in matrix form, and the other one is our HRR form memory. Once we have done the written to the two memories, we transform the HRR's form memories into a matrix form. Essentially speaking, we read every single entry out and then stack them together, forming a matrix form. So that's that. So, and then the following procedures follows exactly the same as the last test, where we have the M prime and the reference memory M, then we compare the difference between the two memories. So that's that. And this procedure has been continued for all the time steps. So essentially emulating the sequential read and write throughout the time. So here are some results of that. So the left figure is the case that where we have the address space of 8 and the dimension of the vectors of 256. In this case, we see that all of the methods where, or I probably should explain that. We tested 3 different codebooks with their corresponding cleanup methods. The crop is that we use the crop codebook with a divide and conquer cleanup method. The sign is we use the binary codebook with a sign-based cleanup method. And last but not least is the none cleanup method with a Gaussian codebook, because if the codebook of the values are Gaussian distributions, then, well, we can't clean it up. So we just have to take it as it is. So back to the experiment. So for the address space of 8 and in the dimension of the vectors to be 256, all of these methods decays in performance throughout the time, yet it is clear to see that our method, denoted as circles, decays the slowest. And the reason why it is not perfect is we hypothesize that is because the dimension of the vector is not large enough for the HRs to be working. And that has been proven by the right-hand side graphs, where the dimension of the vectors has been increased to 2048, so that even the address space is 4 times as big as the previous one. Our method can achieve essentially 100% accuracies throughout the time, which is very good. We also did a different test, since I said before that you have to have the memory, the vectors large enough for the HRs to be worked. So exactly how large your memory needs to be in order for a particular address space size to be working reliably throughout the process. That's basically this test is doing. So here, from our experiments, when the address space is small, essentially here in the leftmost figure, when the address space is 4, then you don't need a very large dimension, but then you still need at least 2 to the power of 8 or 9 dimensions for it to be actually working. And as the address space increases, you need a larger and larger dimension of the vectors for our memories to be working reliably throughout the time. And the largest we have tested is that when the address space of the memories increase to 256, we need at least 2 to the power of 15 of the vectors dimensions for our memories to be working reliably. So crop improves the cleanup efficiency, but it has several caveats or limitations that we have found out. So starting with the first one, take a look at how the codebook has been formed. So assume that you have a current codebook h to the k that contains n of those values, and now you figure out that I have more concept for me to represent as an associate, so that we have to extend the codebook. And the extension, by our definition, is going to be doing something like this. First of all, it is you essentially duplicates the dimension of the vectors instead of canonical matrix formed memories. You just have to add 1 row to the bottom of it. Here you have to duplicate that. And what is worse is that take a look at how you form those codebooks, form the new codebook. You're basically multiplying those trigonometric coefficients. Now here, ck is short for cosine theta k, like in short terms to say some space. Similar things happens to the sk, which is essentially means sine theta k. These red parts are the trigonometric coefficients. So even though we have randomness in the parameter theta k, which is sampled uniformly from 0 to 2 pi, which is 1 period of trigonometric operations, once you have stacked all these trigonometric coefficients together, then that distribution is not as so-called nice as a Gaussian distribution or a binary distributions as we've seen before in the HR's original paper. So we hypothesized that might have some troubles between the current trigonometric stacked distributions and the real-world example. And once we have applied that in the real-world examples, we would expect that to be having some sort of like a distribution mismatch between our codebook and the real-world examples. So that's the first limitation. And the second one is that even though we have a very efficient cleanup method using the divide and conquer, we still relies on the arg math at the very end. And let me remind you that we wanted to apply this memories into a neural architecture, which is end-to-end differentiable. And this argmax might have some troubles if we want to do the back propagations, especially back propagation through time, because this cleanups has to be applied for every single time steps. So that's the second limitation that we found. Followed by the third one that we found is basically, as I mentioned before, that you had to have a large enough dimensions for our methods to be even working. So take a look here. Our method is essentially in the x-axis shifted towards the right-hand side by 2 to the power of 8, by 2 to the power of 7. So for a capacity of memory of only 2, we need at least a memory size of 2 to the power of 8 for it to be working. Not to mention that when your memory capacity grows to, let's say, 2 to the power of 8, then you need a very large vector such that I think the data is 2 to the power of 15. And bear in mind that we wanted to apply that to, again, the neural architecture, which we would naturally assume that the addresses and vectors were produced from the neural network. And just try to imagine that if you wanted to produce a 2 to the power of 15 dimension of vectors from the neural networks every single timestamps, and then how painful that would be when you do the propagation through time, especially. So that would be the third limitation. And last but not least is, technically speaking, our memories is not flexible enough in the case that we don't have type in the data that was stored in our memory. So this is a continuous memory that was used in the NVM that has 3 different pairs of operations: read and write, decrements and increments, and reference and dereference. The latter two pairs of operations are essentially just pointer arithmetics. However, our current model only supports read and write operations. Because we don't have type, therefore we can't do any pointer arithmetics on that. So if we were directly applying that to the NVM, then essentially we're limiting the flexibility of that particular model. So that would be the last limitation that we found in our model for now. So to wrap up, crop is a very efficient cleanup codebook with the linearithmic runtimes for the VSA key value memories. It has several advantages, including, of course, efficient cleanups and also a compact codebook storage because we only need a bigger login storage space and a very efficient vector reconstructions from that, essentially in linear time. But also it has several limitations such as a distributional mismatch potentially from the real-world environments, also non-differentiability because of the argmax, and also following by the high dimensionality requirements. That is being said that you have to have the vectors to be large enough for the VSA key value memories to be even working. And last but not least, it's the we don't have types in the data stored in our memory, so that we can't perform any pointer arithmetics. So essentially that concludes my talk. So thank you for your time. And I believe we could take some questions now. Below us are two QR codes. The the left one is my personal my personal page, and the right one is my advisor's personal web page. So yeah, that's about it.
All right, great. Thank you so much, Rupeng. We have some questions on Discord. We're trying to see. I'm going to try something unusual today. Since we have someone with a lot of questions, we're going to invite him to the lobby and see if that works.
But yeah, while this person is joining, they provided a few comments about that this seems to be related to quantum computing, entanglement, hyperdimensional computing. Do you have any comments on this, Rupeng? Do you agree with this?
I essentially know nothing about quantum computing, but this is basically a VSA method. VSA, in other name, is also known as hyperdimensional computing. So we essentially use this one of those VSA method or HDC methods to form our memory. So yes, it is related to hyperdimensional computing.
Nice. And I see that this person joined. Sorry, I don't know your name. Could you please introduce yourself?
Yeah, hi, I'm Ryan. I'm mainly just a sort of a hobbyist ML person. I was just kind of curious about this approach because I was reading up on hyperdimensional computing earlier. And from what I understand, it seems to be like an alternative approach to machine learning where it achieves feats similar to traditional neural networks, but it appears to be making like different trade-offs, like it is computationally and maybe even conceptually simpler, but it trades that with a lot of memory requirements. What this paper seems to be doing, unless I'm mistaken, is that it's sort of trying to trade some compute in exchange for memory. So instead of like accessing the vectors, you're sort of generating them on the fly, unless I'm mistaken. It's like a compute for memory trade-off, from what I can tell. I was just curious.
Okay, thank you for your question. Let me go back to one of those figures that I may be able to properly explain that. Actually, this one may be perfect. So you were right in the terms of VSA or HDCs here, so that actually I've seen discussions between why use an HDC using such a high dimension, why not you just use embeddings for that? And I personally take it as HDC is a clear way to represent or having more human control in a way to represent a concept related to its representation. So the codebook that you see here is manually defined by us during the process of doing so. So for our method, for example, here, first of all, we're not generating the data out of the blur. We were generating this codebook in the first place, or rather, we were generating those parameters of the codebooks in the first place, and then we were trying to read. Well, we were trying to write things. Write row vectors. Row vectors from those codebooks, writing them into our memory or reading them out, comparing that with our codebook. So that is basically our procedure. So in terms of an alternative way of machine learning, well, it is true in the case of knowledge representation, but I don't think that you can't use them at the same time. That's why we have our current study. I mean, let me remind you that our essential goal is that back to the NVM part where this is the actually I probably should show you this. This is the NVM architecture. It is very complicated, having 3 separate memories, and each of them is essentially using a matrix to represent them. So our major takeaways our major motivations to use HRRs replacing those memories, because those memory computations are expensive, as we have shown right here. And potentially speaking, we thought in the first place then that HRRs or VSAs maybe mitigate that by, you could imagine that flattening out the memories to a single vector, so that the computations of the gradients and all sort of stuff can be more efficiently done. But later on, we realized that you need very large dimensions for our memories to be working, which generates another method, because if you were to apply that in a neural model, then once the neural model produces those vectors, well, if you do the backpropagation through times, assume those vectors are very big in dimensions, then that's going to be very troublesome. So yeah, I'm not sure whether did I answer your question correctly?
Yeah, no, you answered it. Yeah, because I've seen one other paper on arXiv that has a similar approach to yours, although it comes at it from a different direction. Essentially, it's an attempt to reduce the amount of dimensions needed to do the same task, whereas you're doing a different thing where it's like you're making the operations more efficient instead of like trying to cut the dimensions, as far as I can tell.
Mm-hmm.
I think the paper was titled Efficient Hyperdimensional Computing. It may have some level of overlap with yours, but it's probably a different thing. It might be interesting to you. I'm just mentioning it.
Oh, thank you. I'll be taking a look at that.
All right. Well, thanks for those questions. We're at time, but I think kind of building off of those questions, maybe how about zoom out a little bit, and for those in the audience not familiar with VSA, I'll give you a chance to sell VSA overall as a as an approach. Why VSA? What's the attraction? Possible attraction.
Well, to be honest, I haven't thought about that, but my major takeaway of VSA is comparing to a embedding is that the advantage of VSA is basically having a codebook that you can check like every one of those representations. What are those correlated concepts? That gives humans more control, so that if you wanted to do more reasonings on that, then that is a very reliable reference to the comparing that with the embeddings that we have seen in large language models or sort. Other things would be I realized that modern ways of doing VSAs are using this sparse vectors or sparse codebook constructions, so that I haven't looked much into that part, but essentially speaking, the concept was that if you have a sparse matrix or if you have a sparse vector, then you could have some other data structures to store that very efficiently, which means that as long as you can maintain that sparsity, then even though complexity-wise, technically speaking, it is still there, but then during practice, it can be done very efficiently, especially when you're doing a binary, if you're dealing with a binary vectors. So yeah, that's out of the top of my head two advantages that I've been found in the HTC or VSA areas that interested me the most.
And you're building off the neural virtual machine. So why the neural virtual machine?
Essentially, we were trying to, well, the ultimate goal of any AI here is try to build a explainable AI. So we thought, first of all, we have it here, and because this neural virtual machine is one of the papers of my advisors, I see some potentials in that, so that if we were able to train a neural network using this structure, then in some way we potentially could analyze the memory trace of the memory access, so that we are able to know that what the agent is essentially doing. basically trying to produce a program for us to basically trying to produce a humanly readable program so that it's more explainable, comparing to a pure neural network structure, which is essentially a black box.
Okay, but what are the aspects of this model, the virtual machine, versus other, like even the Turing machine, neural Turing machine before that?
Neural Turing machine is basically simply emulations comparing to a neural virtual machine. Because neural Turing machine essentially is just emulating the Turing machine itself, which has limitations of operations in the memory. But then neural virtual machine has shall we say, more modern ways to operate those memories, because we have pointer arithmetics involved in that. So these operations involves referencing and dereferencing, and also increments and decrements, which is good for producing a program. That's my takeaway here.
Sounds good. Are there other questions from the audience, Olga?
No, that's it. But if anyone has questions, please write them on Discord. And Rupen is on Discord, so maybe Rupen can spend a few more minutes after the end to answer any questions to Zarani. But so far, we were good with questions. And yeah, thank you very much, Rupen, for joining us today, for your work.
Thank you.
Oh, apparently there's one more. Can squeeze it through the wire from Michael.
Let me check. Sorry, I missed it. 1 second. There are many. Oh, okay, I see it. On slide 23, you can experimentally see that the dimension is enough. Does this generalize to data that is not sampled from a normal distribution? Can you know the dimension you need without running these experiments?
Pardon me, I kind of missed the middle part of the question.
Oh, okay, let me read it again. On slide 23, you can experimentally see that the dimension is enough. Does enough, in quotes, does this generalize to data that is not sampled from a normal distribution? Can you know the dimension you need without running these experiments?
Well, first of all, the normal distribution is one of our experiments here. So maybe it's a little bit difficult to see here, but there is a little bar here. So basically means that the normal distribution is performing like this is the normal distribution's performance. That we have the codebooks in the from the Gaussian codebook. So essentially. As for how to know that, then we currently only know them by empirical experiments, so that our methods would be working here. As I mentioned before, that having a in a way 2 to the power 7 shift to the right, so that at least you need that big of a dimensions for our methods to be working, and if that doesn't work, then essentially what we can do right now is just testing, testing for a high dimension. Does that work? Or if that doesn't work, then we just have to increase that. So for now, we can only do those. We haven't gone through any analytical procedures to figure out what is exactly the relationship between the capacity itself and the dimensionality of the vectors, which is part of my future work, actually.
Very nice. All right, and with that, call to a close. Thank you so much, Rupeng. For those interested in the broader topic, hyperdimensional computing / VSA / Canurva coding and so on, we'll have a tutorial, hopefully, in a few months in the summer school. All right, thanks everyone for joining. See you next time.
Thank you.